Okay. I'm actually starting with a bit of a trick here. Recursion, which we're going to talk about in the next couple of videos, isn't technically an algorithm. It's more of a concept that we're going to use throughout this section of the course to write some really interesting algorithms. When we get into sorting and searching through our binary search tree, we're going to be using recursion a lot, so I want to prepare you. And obviously, it's also a common topic in interviews. Actually, this is one of the most popular topics, I would say, when it comes to interviewing. Now, what is recursion, really? When you're searching for files on a computer, for example, if you're on your desktop and you want to find all your music files, your MP3 files on your computer, you can't do it by just looking at one folder. You want to look at folders recursively to find all your music. Let me show you what I mean. I have the project here that we've used for one of my other courses, and it's a backend API in Docker. Now I've cloned this repository and I have it right here on my desktop. Now, if I wanted to search through all the files in this project, I can simply type in ls to show me the files. But as you see in blue here, we also have folders that inside of them also have files. How can I also see the files in this folder? Well, I can do something called ls-r. And R, guess what? Stands for recursively. If I do this and I press enter, look at that. I get also the files inside of the folders. You see that I have a controllers folder with JavaScript files. I have Postgres folder with some Docker files, some SQL files. And within those, I also have another folder that has different files. But because I was able to list items recursively, my computer went inside of each folder and printed out the files. So what is recursion? Well, recursion is when you define something in terms of itself. Simply, it's a function that refers to itself inside of the function. All right, there's no way you got that, right? That's probably the most confusing definition ever. Again, let me show you an example. If I open up the console here, a recursive function is a function that refers to itself. So I can create a function called, let's say, inception. And this function is recursive if I refer to itself inside of it. Oops, let's try that again. If I say inception here. This is a recursive function because when this function runs, it's going to call itself and run again. The problem with recursion and why people find it so difficult is that it's an intimidating topic when people start talking about math and theoretical applications. Instead, let's focus here on how recursion helps us solve problems. Recursion is really good for tasks that have repeated subtasks to do. That's it. Kind of like when we looked at the folders inside of this project. And the reason recursion is so important, and the reason that I talk about it first in this section before we dive into all the other algorithms, is that this concept is going to be used in searching and sorting algorithms that we're going to be talking about. For example, traversing a tree, if you think about it, are simply same tasks that we do over and over again. Remember when we build our own tree data structure, our binary search tree? And I gave for you a little function at the end called traverse that allowed us to print our tree so we can verify our answer. If we look at this closer, we see that we're using recursion here. I have a traverse function that calls itself within here. And this is something that we're going to demonstrate a lot of when we talk about searching and sorting in the upcoming sections. Recursion is everywhere. When we do DOM traversal on a website, if we go to elements here, when we do this traversal on an HTML document object model, we're using recursion. In JavaScript, when we have nested objects, so an object inside of an object, well, we use recursion. But the key to getting recursion is to understand that it's not that complex as long as you practice it a little bit. Once you get it and get over the initial hump, then it becomes second nature. And my goal is by the end of these videos that you're going to get recursions. So let's get started. I'll see you in the next one. Bye-bye. Welcome back. I'm about to show you my favorite animation of the course. I'm very proud of it, so don't laugh at me if you think it's silly. I like to think of recursion as this scenario, where you have this tap pouring water into a glass for this little man that's sitting on the couch watching TV. And when I think about recursion, I like to think that they have two big problems. One is that, well, they're kind of difficult to understand at first. The second is that we can have a case like this, where I'm pouring water into a glass, I'm pouring water into a glass, I'm pouring water into a glass, and that is me calling the function over and over and over. And as we keep going, fills up the cup past its limit, it keeps going, it doesn't stop, it keeps calling the function until, oh boy, the man has drowned. What just happened here? This is called Stack Overflow. Let's go back to some code. Remember the function inception that we created? If I run this function and I say inception and simply run this function, I'll get an error. Let's make this a little bit bigger to see. I get an error saying maximum call stack size exceeded. My browser, in this case Google Chrome, is smart enough to say, all right, you got to stop this madness. I'm just calling this inception function over and over and over and over. Because remember, our function just calls itself. And eventually, if Google Chrome doesn't stop this, it's going to crash. And in the past, that's what would happen. If I run this function, the browser would crash and I would have to restart it. But they've added a safeguard here saying, hey, you've called the maximum call stack size. You got to stop what you're doing. Now, this is called Stack Overflow. Why is that? Let's dive deeper into this topic. Just going to clear the console here and write our inception function. But this time, I'm going to add a keyword called debugger that the Chrome browser is going to detect and pause the function when it sees this word. So I'm going to run this function. And you'll notice that as soon as I hit enter, it's going to stop and give me a little panel here where I can control the function. Let's hit enter. And there you go. I'm in now the debugger mode. And you'll see here a few things. One, it'll show me where I am in the function. And also show me, let's change these around just so it's a little bit cleaner. I'm going to make this a little smaller. There you go. You see here something called the call stack. Now from the name Stack Overflow, this might give you a bit of a hint. Right now, we've called the inception function right here. We haven't called it the second time around. If I click on the step over icon over here, it's going to go to the next line of the code. It's going to go to the next, and now it's going to call the next inception function. Have a look over here at the call stack as to what's going to happen next. Did you see that? I just added another function on the call stack. And as we know about stack data structure, we're just adding the function call on top of the older one. And if I step over here and go again, that's a third function call. And if I keep going, you'll see that I'm just adding more and more and more things to the stack. But there's a problem here, right? Nothing's getting popped from the stack. Instead, the function just keeps running, keeps running, keeps running, keeps running, keeps running until we run out of memory here. Remember, stack in this case is grabbing a piece of memory from our computer and adding inception to the stack. And as you know, memory is limited. We don't have infinite amount. So as we keep going, it's going to stack overflow and throw an error. And this is one of the biggest problems with recursion that we're going to get into later on. As you see here though, it can be very, very dangerous because we can run programs that overflow, that never stop, that have infinite loops essentially, that crash our programs. You'll also see here that this costs memory. A stack is holding these function calls. And recursion, one of its downside is that we have to hold on to these calls and remember them one by one, which can get really expensive. So if you ever get asked this question in an interview about recursion, maybe a possible problem with recursion, you can simply say, well, the computer needs to allocate memory to remember things. Stack overflow can occur when we have recursion and there's no way to stop this recursive call. It's simply the computer saying, whoa. Okay, this is getting silly. I'm not remembering any more things. I'm out of memory. I am going to just error out. In the next video, we're going to try and solve this problem and learn about something called a base case, a thing that you have to have in a recursive function to stop it from doing this. I'll see you in the next one. Bye-bye. Every recursive function needs to have something called a base case or a stop point. Remember my example at the beginning where I showed you how to recursively check out all the folders in one of our projects? We have to tell the program, hey, if the subfolder we're going to no longer has any more folders, stop. If this stop wasn't there, the function would just keep running. So recursive functions have two paths. One is the recursive case, that is, call the function again and run it. And then the base case, that is, stop calling the function, there's nothing more to search. So how can we add this feature of telling the function, hey, quit it, you're being ridiculous right now, you need to stop? Well, we can do something like this. We can create a counter, and we'll say this counter is 0. And we can add a conditional statement. We'll say that if counter is greater than 3, in that case, just return done. Otherwise, we'll call inception, but we also want to increment the counter by 1. So if I click run here, well, I have to call the function first. Let's say inception. If I call this function right now, what do you think will happen? Pause the video, think about it, because I'm about to click run in 3, 2, 1. I get undefined. Is that what you expected? Just to show you something, if I comment this code out and we just do this inception, where we just keep calling inception, and perhaps do a console.log here saying hello, and I click run, I get maximum call stack size exceeded. Okay, we know by looking at this function, this version of the function, that it's never going to get to console.log because as soon as it hits the first line of the function, it's going to go back and say, oh, I'm calling this. And then it's going to go here. It's just going to bounce back and forth, never getting to console log. But if we go back to what we had before, well, our function clearly has ended. It hasn't done Stack Overflow. And at one point, it's ended because we increment the counter. So let me console.log here our counter. and make sure that this works. If I click run, I get 0, 1, 2, 3, 4. When it gets to 4, counter is greater than 3, so we're returning done. But why is there no done here? And this is a great illustration of how recursion works. I'm going to copy this code and go back to our browser over here. Let me refresh this page to make sure that we have a clear global variable. And I'm going to copy and paste inception. This time around, I'm going to add the debugger keyword so that we can debug our code and go step by step through it. Let's run inception and see what happens. All right, we're back to our debugger. We see that we have the call stack here. Inception has just been called by me. And I also opened up this little tab called scope. For our case, we want to just open up the script scope. It shows us what variables we have available to us. In this case, we have counter, which is 0. So I'm going to click step over, and it's going to say, hey, we have counter is equal to 0. Is that greater than 3? Nope. I'm going to skip over, increment counter, and run inception. We see that that happened. Counter has now been incremented because we've gone through this line, and now we go to inception. We're going to run the function again. And you'll notice that the call stack, when I click this, is going to increase. Perfect. And we're going to go one more time. Counter is now 1. Nope. Don't return anything yet. Increment the counter. You'll see counter goes to 2. And we're going to run inception again. And we keep going once more. Passing through. Counter becomes 3. Adding inception to the stack. And then one more time. 3 is not greater than 3. So we go one more time. Calling inception. Adding it to the stack. We now have these many stacks. Counter is at 4. And then we step over here. Counter is now 4, which is greater than 3. We're finally going to enter the if condition. That's going to return done for us. Let's see what happens here. I'm going to click next. And I click next again. Look at that. We have a local variable now that has return value done. We've now returned done, and we're no longer going to call inception. The call stack is now going to start popping off these functions because it's going to say, oh, we have a return keyword. I'm going to stop whatever I'm doing at the bottom here and return from this function. So this inception function is going to get return done. But notice what happens next. Oh, I get return value undefined as we popped off the top item from inception from the call stack. And if I keep popping things from the call stack, the return value is undefined, and that's what we get. Now, why is that? Well, if we go back to our function, what you just saw was us essentially doing this. We called inception once, twice, 3 times, and then 4 times. And within here, when we finally got here, we said, oh, return done. So this inception function turns into done. And then we go to this function. Now, the problem with this, and I know this can get confusing, is that once we've returned once, we've popped off the stack and we're now at this part of inception. But this inception never returns anything. When a function doesn't return anything, it just returns undefined. So we need to keep telling it to return this done and bubble it up towards the very end. And this is something that you have to keep in mind with recursion. There's usually a base case, and you always want to make sure you return so that the value that you want gets bubbled up all the way to the top. In our case, all we need to do is say return inception. This way, this inception knows to return whatever its result was, which was done. And this inception knows to return whatever this result was, which again is done. And so on and so forth until we get done back. Let's run this again. And I have to call the function. Let's do that again. Inception. And run. And we're done. Very, very nice. If I go back here and go back to the console, I encourage you to try this out, this time adding the return keyword to inception and running through the debugger to see what happens. But what I just showed you is all you need to build recursive functions. You have 3 rules. 1 is to identify the base case. 2 is to identify the recursive case. So we've identified the base case, when to stop, the recursive case, that is when counter is less than 3. And then finally, our third step is to get closer and closer and return when needed. And that usually you have 2 returns for the base case and the recursive case, because you want to return something at the end of the function. So let's comment this out. We have an idea of how recursion works. The function simply gets closer and closer and closer to the base case, and once it gets to the base case, it finally returns and pops functions off the stack. But that's enough talking from me. I think it's time for us to do some coding exercises to get really familiar with this topic. I'll see you in the next one. Bye-bye. Welcome back. I have a fun little exercise for you. And now you're asking yourself, Andre, you say all exercises are fun. You're a big liar. All right, fair point, but I think this one's going to be fun, so stick with me. I want you to write a function, actually 2 functions, that finds the factorial of any number. Now, why 2 functions? Well, one function is going to be recursive, using what we just learned, where we have to create a base case. We have to follow the steps, right? If we go back, we have to identify a base case and a recursive case. And then finally, make sure that we return both cases. So this recursive function is going to return an answer. But what is a factorial? A good way to think about factorial is this notation, 5 exclamation mark. Factorial simply means multiply 5 times 4 times 3 times 2 times 1. You keep going down one by one, multiplying each number until you get to 1. So 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And you'll notice here that it's a recursion pattern that we're doing. We call the function and we have 2 cases that can happen. We have the base case to stop or recursive case, and so on and so forth. And we keep going until we hit 1. So I want you to build a function that does this for us. I'm going to write the function factorial. You're going to put in 5, and it's going to run through this. But remember our definition of recursion. Recursion is when you define something in terms of itself. Now, a good way to think about factorial is this. 5 factorial is simply 5 times 4 factorial. You see over here, 5 times 4 factorial is factorial 5. 5 times 4 times 3 factorial, 4 times 3 is 5 factorial because 4 times factorial 3 equals factorial 4. And you see here how we might have a recursion function that we can write. Using this knowledge, see if you can create a function that allows you to do this. Now, when it comes to this question, there's 2 ways that you can go about it. You can do the recursive approach, where the function calls itself, or you can do the iterative approach, which means looping. And most of you are probably going to find it easier to solve it with this way, with just a for loop, for example. I'm going to leave this up to you to figure out. See if you can do both functions and see if they give you the right number. And in the next video, I'll show you the answer. I'll see you in that one. Good luck. Welcome back. Let's start off with the iterative approach. That is, no recursion. If we want to run the function, let's say find factorial iterative 5, well, we can create a variable, let's say answer. And for now, this answer will be 1. And all we're going to do is do a for loop. We'll say let I equals 0. Or, in our case, to simplify things, let's start at 2. And I'm going to explain in a second why we want to start at 2. I'm going to say I is less than the number. And then we're going to increment I by 1. Now, why are we starting at 2? You might notice a shortcut here. 1 factorial is just 1. 2 factorial is 2 times 1, which is just 2. So these last 2 bits, if somebody says 1 factorial or 2 factorial, we can just simply return the number that they've entered because there's no real calculation that we need to do. So this is a little shortcut so we avoid extra loops by just saying that if the number that the user enters is, let's say, 2, so that is 2 is not greater than number 2. The way we have it now, if somebody enters find factorial iterative 2, we're going to return 1. But instead, we can just say maybe a simple conditional check saying that if number equals to 2, we'll just say that answer equals to 2. So that if I run this function and just say 2, I get 2. If I say 1, I get 1. And there's other checks that we can do, obviously. But for our case, this is good enough. Let's look at what we can do inside of here. Well, the way factorial works is to simply say answer is going to equal answer times I. So that if I click run here and let's do 5, I get 24, which is actually not the right answer because 5 times 4 is 20 times 3 is, well, clearly higher than 24. And that's because of a little mistake here. We want to make sure that this is equals because we want to include the number 5. So if I run this again, I get 120, which is the right answer. 5 times 4 is 20 times 3 is 60 times 2 is 120 times 1 is just 120. Perfect. So hopefully you got that answer correct. What about the recursive approach? In the recursive version, we'll just do a simple check saying if number is equal to 2, and we can do other checks as well, but that should be enough for now for us to create a base case. So if the number gets to 2, we'll just return 2. There's our base case. That's how we stop. Next, we're going to return our recursive version, which will simply be number times the function. And in this function, we're just going to say number minus 1. And that's the key here. We want to always get lower and lower until we hit the base case. So if I hit run here, let's do recursive this time. I'm going to move this up over here. And if I hit run, I also get 120. And this is a little hard to wrap your mind around. So you might want to copy this code and open up Google Chrome Developer Tools like I showed you and go step by step. But if we start with the number 5 here, well, does 5 equal 2? Nope. Then we'll say 5 times find factorial 4 should be our answer, just like the diagram that I showed you. And we keep going until we hit the base case of does the number equal 2? Now, one last bit. What do you think the time complexity of these two functions are? Well, one uses a for loop, with the loop being the number associated with it. And we're doing a bit of a shortcut here, so it's technically less than O of n, but because of our big O rules, this is still going to be O of n. The recursive function, if we look at this, we are looping how many times? Well, we're calling the function find factorial recursive the same number of times as the number itself. So this also becomes O of n. If you got this question, good job. It's a tough one. If you didn't, don't worry. We have another one coming up. I'll see you in the next one. Bye-bye. Welcome back. You can't talk about recursion without talking about the Fibonacci sequence. What is the Fibonacci sequence? Well, it's this sequence right here. The pattern, if you notice, is that we're always adding the first two items equals this one. So 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, so on and so forth, so on and so forth. So the previous two numbers always equals the current number. So I have another exercise for you. This one a little bit tougher than the previous one. Given a number n that the function is going to receive, return the index value of the Fibonacci sequence. So if I say that I want the n to equal 2, it's going to give me 0, 1, 2. That is the number 1. This function is going to return 1. If I say Fibonacci number 8, I would get 0, 1, 2, 3, 4, 5, 6, 7, 8. I would get 21. The function will tell me what number is associated with the index that I give it. Once again, I have the iterative approach, that is using just simple for loops, and also the recursive approach. I challenge you to try both of these and see if you can do it. And a big hint here is that the recursive approach is actually easier than the iterative approach. So good luck out there, and I'll see you in the solution video. Bye-bye. Welcome back. How was that exercise? Does your brain hurt from all this confusing sequence? Let's actually start off with the recursive function this time. Because in this case, the recursive function is actually a lot simpler to think about. All we would do with our recursive function is to say, well, the base case is going to say number or n is going to equal 2. If that's the case, simply return. Actually, if we look at the sequence, we see that if the index is 0, the answer is 0. If the index is 1, the answer is 1. And if the index is 2, then the answer changes to 1. So instead, our base case can maybe just simply be if n is less than 2, we're always going to just return whatever the n is. So if we say 0, it's going to return 0. If we say 1, it's going to return 1. If we have an index higher than that, well, then we have to do some recursion. And all we're going to do here is have another return statement and say this function. I know that this function is really long. We can probably make it shorter to just say fib. And I noticed that we don't need the iterative here. That will make it a little shorter. There you go. And all we're going to say is fib is going to equal n minus 1 plus the same thing n minus 2. Because remember, the sum is always, the answer is always the numbers 1 and 2 before it. So we're just adding the numbers 1 and 2 before our sequence. And that's it. If we run this function, let's say Fibonacci recursive of 3, and I click run, I get 2 because 0, 1, 2, 3 is 2. Let's do 8, which should give us 21. And I click run, or give 8, I get 21. Nice. And if I do 0, I get 0. If I do 1, I get 1. If I do 2, I should get 1 right here. Nice and simple. Well, I don't know about simple, right? You really have to get comfortable with this before you truly understand what's happening. But I have a little diagram to help you here. All we've done is simply this. If I added 7 here, our recursive function is going to get 1 less than 7 and 2 less than 5. And then within those functions, do the same thing. 1 less than 6, 2 less than 6. 1 less than 5, 2 less than 3. And it's doing all of these until we get to fib of 1, 2, where we have our base case that returns that number. So this becomes 1. This also becomes 1, and then it keeps going, keeps returning until we get to fib of 7. Now this is a diagram that we're going to get back to, but you see we're doing a lot of calculations here. But simply put, this is all we're doing. Now I said that the recursive approach is actually simpler than the iterative approach. Let's have a look at what the iterative approach would look like. We'll create an array, and there's many ways of doing this. This is my preferred way. And this array is going to have the initial items of the sequence, 0 and 1. And this is going to, first of all, return the array and item of n. We're creating this array and then grabbing whatever index the user wants. In our case, if the user requests 0 or 1, we already have the array pre-filled with 0 and 1, and it's going to return the same. But we still need to calculate for all the other ones. That's where we do a for loop and say let I equal 2, because we're going to start adding when the index is 0, 1, 2 to start filling this array. We'll say I is less than n plus 1, or we can do equals here if we want. We'll leave it at that for now, and we'll increment I++. And in this loop, we're going to keep going until we hit the number of index that we're interested in, and all we're going to say is array.push array I minus 2 plus array I minus 1. Similar to what we did before, we're just summing the previous two numbers and pushing it to the array. All right, now let's see if this works. I'm going to comment out this one and just do the iterative approach. I get 2 for 3. What about index of 8? I get 21. Perfect. And then if I do index of 0, index of 1, and index of 2, should be 1. Perfect. Now, I said that the recursive approach is simpler than the iterative approach. Now, that's my personal opinion. You might not think that. You might think that this was quite easy. But to me, this reads a lot nicer than all this thing that we're doing. And this is something we're going to get into in the next video, where we talk about the trade-offs between the iterative and the recursive approaches to these problems. And why, maybe you're wondering right now, why would we ever write anything recursive if you find this confusing? We'll get to that. But the one thing I want to show you is something that we just learned here that is new to us. What do you think the big O of these two functions are? Well, in our iterative solution, the big O is linear time, right? It's O of n. Basically, we're just iterating through the loop n minus 2 times because we're skipping the first 2 items, which in turn makes it O of n. But what about the recursive approach? Remember the diagram I showed you? That's a lot more calculations than just the 7, right? We have a lot of function calls that happen. In this case, in the recursion solution, it takes what we call exponential time. The size of the tree exponentially grows when n increases. If Fibonacci number was 8, we would have this tree as well as another tree underneath the fib of 8. So what is the big O of that? This is very exciting because we're learning about a new big O notation. We're learning about this one, exponential time, which can be seen with recursive algorithms that solve a problem of size n, 2 to the power of n. If we go to our big O cheat sheet, this is O 2 to the power of n. You see how much it increases? That's pretty bad. It's bigger than even O of n squared, the 2 nested for loops. Exponential time means every additional element in the Fibonacci sequence, we get an increase in function calls exponentially. And here's a fun little trick. Although this is O of n, the iterative approach, this function, because it's O of 2 to the power of n, if I run this function, let's say if we do 10, I get a result. If I do 15, I still get a result. What if I do 20 here? All right, it's starting to get bigger and bigger. If I do 30, if I do 40, do you see how much longer that took to calculate? Because our time complexity is increasing more and more. If I do 43 now, you'll see that we're waiting and waiting and waiting for the calculation to happen, and eventually the browser comes up with the calculation. As a bonus question, think about how many calculations Fibonacci 43 required. This, although might be more readable, is not an ideal solution. As you can see, big O time complexity is pretty big. And this is something that you might get asked in an interview. And I know what you're thinking. Andre, you just taught us about recursion and it's not even good. It's slow, it's confusing. Why would I ever want to use recursion? In the next video, I'm going to talk about this trade-off. Why would you ever use recursion over something that is iterative? Why would any sane person do that? And as you'll find out, there are some pros and cons. And as a matter of fact, a function like this, such as Fibonacci sequence in recursion, can be made to O of n using something like dynamic programming and memoization, which we're going to talk about towards the end of this course. And we're going to get back to this. But let's finally answer the question in the next video. Why would you ever use recursion over something iterative? I'll see you in the next one. Bye-bye. Welcome back. There is a theorem that states anything that can be implemented recursively can be implemented iteratively. That is, you can go your whole life without implementing recursive functions and just use loops. Okay, so why would we ever want to confuse ourselves with a topic like recursion that can be a little confusing? Well, for some problems, it's actually easier to write, but it really depends on the situation. Keep in mind that there's always two options. And by now, you know that with programming, there's always pros and cons. And a good engineer is somebody who can make the right decisions based on those pros and cons. But I want you to keep this in mind for interviews, because interviewers will ask you to solve a problem. And a problem that can be solved with recursion can usually be solved iteratively as well. And looking at our Fibonacci function, this is a simpler example of recursion. But there are times when recursion can keep your code dry. That is, do not repeat yourself. A big rule when it comes to programming. And there are a lot of problems when it comes to recursion as they get harder and harder when using recursive functions allow your code to be more readable and also dry, simpler, have less loops happening with confusing code. And I'm a little bit biased because although recursion is a powerful technique, in my opinion, it's not always the best approach. So you need to make sure because of, or its main drawback. That is, although recursion can keep your code dry and make your code more readable, it also creates this extra memory footprint. Because every time we add a function to the call stack, it adds extra piece of memory. So you have cases where you can get stack overflows. Or if your system has expensive memory, you want to avoid making too many recursive calls. And for some people, recursion is also something that is hard to wrap their mind around. And if you have a team of young engineers, of developers that aren't familiar with recursion, that may not be the best option. But the main drawback is this, that iterative approaches tend to be more efficient because they don't make these additional function calls that take up the stack space, with the downside being that iterative solutions might be not as readable. And a rule that I like to follow is that I like to use recursion when you're working with data structures that you're not really sure how deep they are, where you don't know how many loops to go through. And as you'll see, recursion is really useful for things such as tree data structures and doing traversal because that is often the case. Now, in the next video, I want to talk about this topic a little bit deeper and when to use recursion. But I do want to point one thing quickly. There's something called tail call optimization in many languages. And for example, in JavaScript with ES6, it allows recursions to be called without increasing the call stack. You can read more about it in the resources that I'll provide to you in this video. But in other languages as well, there are certain ways to write recursions so they're more memory efficient. So this large stack issue can actually be resolved during production. But let's talk about a definitive guide to when to use recursion in the next video. When should we use recursion? This is the rule that I like to use. When it gets to complicated problems like traversing or searching through trees or graphs, something that we're going to talk about with breadth first search and depth first search, recursion is really, really useful and better than iterative approaches. And with sorting through items, there's also cases that we'll see that recursion is preferred. And when it comes to recursion, these are the rules that I like to follow. Every time we're using a tree or converting something into a tree, consider recursion. And there's 3 key things in an interview question that might trigger a recursive solution. One is that a problem can be divided into a number of subproblems that are smaller instances of that same problem, such as the exercises we've done with Fibonacci numbers or factorial. We can break those down into little trees that break down to smaller and smaller pieces. Those are inherently recursive problems. Another factor is that each of these instances of subproblem is identical in nature. That is, the calculations that we need to do are pretty much the same. They may be smaller values, but the actual calculations underneath it is all the same over and over and over. And then finally, the third point is that those solutions, if you solve the smaller problems, the leaf nodes of that tree, and you combine them, that solves the problem at hand, then that is a recursive solution that you can use. And you'll see a lot of divide and conquer using recursion. Remember divide and conquer, which we mentioned when we got to the tree data structure lessons. It's kind of like looking through a phone book. When you're looking for Bill in the phone book, you're not going to start from A and simply go one page at a time from left to right. No, you usually split the phone book in the middle or try to go to the B section of the phone book and start dividing up the problem page by page until you get closer and closer. This divide and conquer type of questions usually have recursion in them. And as we know, the one thing that recursions can do that looping can't is that they can make tasks super, super easy, such as these types of problems. As a matter of fact, I encourage you to write your own traverse function that we use in our tree data structure. This is something that we're going to get to when we get to searching in the algorithm section. But if you want to challenge yourself, see if you can write a traverse function like I did over here using recursion. And then also try to write it with loops. You'll see that with loops, things like tree traversal is a headache. I can't even do it from the top of my head. With recursion, it's pretty straightforward. With loops, you usually have to maintain some sort of a stack to keep track of things. And it really adds a lot of complexity. So use the rules below to notice when a recursive problem presents itself during an interview. I'll leave a few more exercises for you after this video. But as we'll see, we'll come back to this topic when we get into other algorithm sections. And things will start to get clearer and clearer. I'll see you in the next one. Bye-bye. When we talk about recursion in computer science, we're talking about a function that calls itself. This type of technique is really good at some problems because of its ability to maintain state at different level of recursions. Just like our couchman watching TV here, recursion can be thought of as a bit of glass that gets filled up with recursive calls of functions, and then we start popping from the top until the very last function gets popped off and returns a value. One thing that we want to be careful of with recursion was this idea of stack overflow, this added memory space, as we keep calling the same function over and over until we possibly can reach a limit and get stack overflow. The rule of thumb that we learned is that we should use recursion when it makes code more readable. But sometimes it can be less efficient than iterative or looping solutions, so we have to be careful. We also learned the rule that anything you do with a recursion can be done iteratively. And in interviews, you'll get asked the question of the pros and cons of why we might want to use recursive over iterative. And I know I've brought this up before, but it's worth repeating. Recursion is interesting and clever, but can be costly, so you have to be really careful with it. Because recursion and space complexity are not friends. But when it comes to some problems like sorting and tree traversal, you'll see that we're going to have to use recursive solutions to make things simpler. Specifically, when we talk about these upcoming topics, we're going to be using recursion. So get ready for it. Merge sort, quick sort, tree traversal, graph traversal, all use recursion. Now we're equipped a lot better to handle those situations that are going to come up.